Hello. As mentioned, I am Emily, and it's a huge pleasure to be here today at Serverless Days. It's the first kind of serverless-related conference I've spoken at. There's been some awesome talks today, so I hope I don't bore you in the last few hour of the afternoon. But yeah, today I'm going to be talking to you about building real-time-ish data pipelines with AWS. This time last year, I was tasked with a particular customer problem that I needed to solve. Was not familiar with SQS at all, so I had to look into that and figure out what a solution would be to build a real-time-ish data pipeline. So I'll track you through kind of what I learned, the sort of trade-offs I had to make, and how I got to a real-time-ish data pipeline. So first of all, though, who am I? Well, you know that I'm Emily, but I'm also a horse rider. This is me on my horse Tonic. He couldn't be here today, sorry, but you know, he says nay. But aside from riding horses, I am actually a data engineer, but I kind of turned into a full-stack software developer and everything in between because I've mostly worked in startups, which means you wear a lot of hats. So some of those startups, I have built data pipelines for rocket engines at Rocket Lab, cows at Halter, and now developers at Multitudes. So a bit of a vast experience of data products, but I really love it. When I joined Multitudes, though, I was the first technical hire. Our tech stack was Python scripts that I ran on my computer, so I very quickly had to upskill in what is an API, how to build an API, and this kind of new serverless space. So I was in quite a unique position because I was a data person, so suddenly I had to be the one building the APIs that gave me the really deliciously nested JSON that I absolutely love having to process. So now I could build those APIs. Could I make those APIs a little bit better to give me the data that I want? So fast forward 4 years. I'm now the staff engineer at Multitudes. I run the dev stack and the data stack, so that means I get to combine the best of serverless and data engineering to hopefully make good data pipelines and a good data product. But on that note, a little bit of context about what we do at Multitudes, because that will help for my talk, since that's what I'm talking about, is that we are a company that provides engineering metrics that aren't creepy for software development teams to hopefully improve team collaboration, performance, and well-being. But we really focus on the collaboration and well-being, and then performance comes secondary to those. So in order to do that, we process a lot of data from some tools that some of you probably use. We've got GitHub, Jira, PagerDuty, Linear, Opsgenie, just to name a few. We fire a whole bunch of data into the magical Multitudes platform, and then out pops some nice shiny insights, actions teams can take to help them improve. So that's a little bit about what we do at Multitudes, but today I'm going to be focusing specifically on a pipeline I built for GitHub. We had an awesome talk about GitHub earlier, and so today I'm talking about a particular customer problem that we need to solve. So what was that customer problem? Well, we want to be able to see which pull requests most need our attention right now. In a large organization, there's multiple teams and there's lots of pull requests coming in. The best way to speed up how quickly your code gets into production is to hopefully merge some pull requests and get them out. They can be delayed because they're waiting for a review, they're still in draft, or the developer got stuck on something else and so it's just kind of sitting there. Believe it or not, this is not something you can do in GitHub. You can see the pull requests assigned to you. You can see pull requests on a certain repository, but there's nowhere where you can centrally see all the pull requests open and how you can help. Oh, that was fun. This becomes particularly problematic if you use microservices, which basically just means repositories everywhere. I know at Multitudes we are microservices. There's 94 repositories that we have. So trying to look at all of those pull requests is just really, really hard. So this would be the ideal solution. You know, you can see a nice table of all your pull requests, how long they've been open. This is actually real data from like Tuesday at Multitudes. We've got a big feature launch coming up on Monday. how long has it been open, what state is it in, and some additional metadata. So yeah, how can we deliver this to customers in a way that is up to date so that it actually reflects what your current teams are doing? So the first thing I like to do as a data person is it really determines how you build something as to like what the actual customer requirements are. It's really easy to get down deep in the weeds to be like, oh, what's the most amazing data pipeline I can build to be like super fast? But that's not always what's required from customers. So number one, right now, pretty important, we expect the list of pull requests to be reflective of what's happening in GitHub right now. But that doesn't necessarily mean real time. What I would expect is I close a pull request on GitHub, and that pull request should then disappear from the table, or I update a pull request and I should see that information reflected. So really we're talking maybe about a second or two that we have to have data updated. Secondly, we are very careful about data privacy and security at Multitudes, so everything is very customer specific. Usually customers' data is processed separately, just so that we don't have any data leakages or anything like that, and we try to segregate it as much as possible. Also, obviously, we only want to be showing customers their pull requests, not someone else's. And lastly, we kind of can't not be accurate. You could literally go look in GitHub to see how many comments the pull request has or if it's open. So, of course, we need to be accurate and in sync with what GitHub is doing. Now, I know what you're thinking. Emily, isn't there an API though? This is GitHub. There's a REST API. There's a GraphQL API. Why am I even doing this talk? Well, a little fun thing about GitHub, when you are an organization that integrates with it to then integrate with other organizations' GitHubs, is that there's actually a global rate limit on the API. So we found that out the hard way. And when you hit that rate limit, you're locked out of GitHub for an hour. We need to use that rate limit for other things like historical batch processing, which is fine. We can wait an hour for historical data processing, but if the pull request table is down for an hour, that's not so great. So basically, using the API was out of the question, and we already are processing GitHub data, so how can we augment that pipeline to get what we want? Well, what is the current pipeline? So this was the very first thing I built at Multitudes. Basically, GitHub provides a way to get a webhook to send data from a customer to somewhere. Obviously, it makes sense that this is a Lambda, put a little API gateway on it, GitHub fires the events there. This is the very first Lambda that I built. It is still alive in Multitudes today, still the ultimate MVP, like dealing with tons of events a millisecond, doing a great job. So this basically captures the GitHub events, verifies that they come from GitHub, and makes sure we can then send them into Snowflake. So we use Snowflake for our data warehousing. Obviously, that's not serverless, but got to talk about it anyway. Pipe them in, use DBD to transform the data. And then we spin up an ECS task in Python, grabs all the data, processes it, enriches our custom metrics, adds some metadata, et cetera, to make the data available for what Multitudes needs. Then that gets chucked into an RDS database, also not serverless, but we have a lot of relations, a lot of data, so a Postgres database was the most suited for that. And then APIs sit on top of that, which also aren't serverless, but that's what serves our application. So the only issue with this pipeline is that it's still kind of old school and as a batch process. I'm getting there. So it only runs every 6 hours. So if we were to pull the data from this pipeline, the pull request information could be up to 6 hours behind, which is not really great and all what the customer wants. So the first thought was, can we just run this all the time? Just process the data as fast as possible. And that wasn't really a feasible solution for cost reasons. There's a lot of other data that we process, like commits, comments, et cetera. We just want to get pull requests, so not really a possibility. So then what are our options? Well, I kind of looked into 3 main options. I hadn't settled on SQS necessarily. Just wanted to see, like, okay, I've got to move data from here to here in a fast fashion. What can I do to do that? Number 1, obviously Kafka. We just heard a great talk about Kafka. Then there's also Kinesis Firehose. And lastly, I looked into SQS. I had 2 weeks to build this pipeline. I don't know Java or Scala. Kafka, quite frankly, is terrifying. Don't want to deal with clusters. I know there's AWS managed Kafka, but didn't really want to try that. So I just ruled it out. So this is too hard. No, thank you. The second one is Kinesis Firehose. Did some like basic back of the envelope calculations and was just like, oh, that's just going to be too expensive and maybe too hard. So I was a little bit scared by the streaming word. I'm maybe more of a hater than a lover of the streaming. So basically set it on SQS. It seemed to be able to do what we needed to do. This seemed like a pretty good option. May as well try it, see what happens. The good thing about SQS is it's a nice queuing service, so queues your messages for you, and then you can just spin up a whole bunch of Lambdas, do the things you want to do, and then you kind of get into the situation of like Oprah, like you get a Lambda, everybody gets a Lambda, it's a great time. We are not big enough to hit the concurrency issue, so I'm still in the like everyone gets a Lambda space. I'm sure that's coming from Michael's talk, so I look forward to that day, but at the moment we're like Lambdas everywhere, it's great. Then with those Lambdas, we can very easily chuck them into something like DynamoDB. With on-demand read and write, we can just kind of chuck them in there and they'll be kind of sweet as. So I was like, this seems like a good solution. We'll try it, look at some metrics, see how it goes. So chuck the pull requests into DynamoDB, put an API on top of that, see what happens. Now with SQS, it's important to think about what kind of queue you want. So I had to research all of the documentation about like, what are the differences? So we've got the standard queue, again, pretty standard. Events come in, it's at least once processing, so there may be duplicates. Order is not guaranteed. You also have to handle kind of batching and like how many Lambdas you spin up, etc. Secondly, there's a FIFO, so first in, first out queue. That means events are processed as they come in and the order is preserved, and it also guarantees exactly once processing. In addition to FIFO, there is also a variant of that called a FIFO high throughput. So if you're expecting a lot of events coming in, you can put it into high throughput mode and it will handle it a lot better. So for our case, we're talking about an event coming in potentially every, like 300 events a second potentially. And then it's every time someone like comments on a pull request, edits a pull request, opens a pull request, closes a pull request. We have about 50 organizations at the moment. Each of them have anywhere from 50 to 200 developers, so you can see how we could potentially have a lot of events coming in at certain periods of the day. So just went with the easiest one of like, we'll just do the high throughput, it'll be fine. But it's really important to also think about what those limits are. So you can do 70,000 transactions a second. As I mentioned, we do about 300 a second, so 70,000 seems pretty good. 256K maximum payload size. Your average pull request on GitHub is about 90 kilobytes, so pretty good there. And then you can have 20,000 in-flight messages, which just means that your Lambdas need to be fast enough to process the messages. All we're really doing is some basic analysis, math, a couple of things on the Lambda, and then putting it into a DynamoDB, so we don't have to worry too much about how long it's taking. So, you know, she'll be right, mate. All good, no worries. Then what does that look like now if we think about our pipeline and how this will work with it, noting that our other pipeline is live, so I was a bit too scared to modify that main Lambda too much since it is the core of multitudes. So basically we still have our original pipeline, GitHub firing events in, those events going to Snowflake, but now we can apply a filter and make sure that we send pull request events only into the queue. We then have a nice little Lambda that pulls from that queue and then saves them into DynamoDB. So this was pretty great. We set this all up, and I'll go through a little bit about some of the parameters that I had to look at when setting up the Lambdas and the DynamoDB. So in terms of the sending Lambda, I had a pretty simple job, just like throw the event, it's fine. A little bit of what that code looked like. So if it's not a pull request, don't care, don't send it to the queue. And then stringify some stuff. This is all in TypeScript. But the most important things to think about with a FIFO queue is the message group ID, which is how it batches the events together. So it guarantees sequential processing, so like everything in order, but inside the message group. So I don't really care if organization A and organization B's events are processed out of order, but all of organization A's events need to be processed in order. So It also ensures that a Lambda is spun up and it batches the message group's messages only. It could potentially add other ones, but that's a whole other thing. But it just means we can keep the data together. The deduplication ID is also important. With FIFO, you can't do content-based deduplication. You have to do by the message group ID. So with this one, GitHub provides us an event ID that is unique based on the pull request event that is sent. So it makes sense to use that. So if GitHub for some reason sent us the same event twice, the FIFO queue would handle the deduplication of that. But also, it wouldn't really matter too much. We'd just be processing an extra event. In terms of the DynamoDB table, the Lambda that reads from the queue is pretty straightforward. The code's online for that. It basically had to read from the queue, put it into Dynamo, but how you set up your DynamoDB table is somewhat important. So I love Terraform. We Terraform everything here. So this is a little pull request table, Terraform. Love the AWS official Terraform modules. If you're new to Terraform when you're on AWS, highly recommend checking that out because it kind of abstracts all of the hard stuff away for you. So literally to make a DynamoDB table, I just have to provide this. Some of the most important fields here, kind of ignore the other ones, is the hash key and the range key. So hash key is how the data is partitioned. Obviously you want this by organization ID. That is how your reads and writes are managed as well. So it means you can read and write the same organization without impacting others. And then the range key, this was to do with how we wanted to write the data. So obviously, we wanted to do an update on a unique pull request ID. So therefore, we set our range key to that. So therefore, it's a unique key. And every time we call an update, it knows to either create it or update it, which is quite nice. But then in terms of how the API accessed the data was that it pulled the latest open pull requests. So we therefore made a local secondary index that would allow us to search an organization and the updated ats of the pull requests themselves, so we didn't have to do too much stuff there. And then lastly, TTL is a really cool feature of DynamoDB that's time till live. What you can do here is DynamoDB will automatically delete your data for you after this time period has expired. So we only really wanted to save 2 weeks of data. If you haven't updated a pull request in 2 weeks, then you probably don't really care about it. We have another function of the app for that. So with this, you can say, OK, delete the pull request in 2 weeks if there's no update. And that kind of keeps our table at a smaller size. We don't store all pull requests forever that were open. So yeah, highly recommend looking into that. You just have to set a TTL attribute and say at what point the item will expire. So this went out into production. It was all good. The most important thing about building a very simple data pipeline is knowing if it's working. And as a data person, I want to know what are the numbers? How are we going? So over the last 3 months, the oldest message age ever was 3 seconds. On average, it was about 1 second. So that means the longest amount of time it took for a pull request to be updated in our system was 3 seconds, which really is fine in the scheme of humans because we only really care about, in the seconds, not in the milliseconds. We're processing about 100 messages a second. I know that's not much in the scheme of some other companies here today, but it just goes to show, this was a perfectly good solution for what we needed. We're not big enough yet to need some fancy streaming service, so it's perfect for what we need, and hopefully we'll be able to scale until we hit fun Lambda concurrency limits. So far, we've had no errors, no DynamoDB issues with reading and writing. We use on-demand read and write for DynamoDB. We don't provision any read and write concurrency. We just kind of let it do its thing, and that seems to be working so far. And then lastly, the most important thing is the cost. Now, there's a learning later on in this presentation, but I did not tag my resources very well in AWS, so it was kind of hard to figure out what the cost was, because we have other SQS, other DynamoDBs, but it was about under $5 a month, which was pretty good in terms of other streaming services. So what were my learnings from that? 1, put good monitoring in place. That's very important to know that as your queue performing as it should, or your Lambda's doing the right thing, as your pipeline's struggling. 2, as I mentioned, think carefully about how you group messages and deduplication. That is really important to maximize your queue efficiency. Keep it simple. This was a very, very simple solution. I could have made it more complicated, but it works for the purpose. AWS permissions are always fun. As the saying goes, there's always a permission missing. So yeah, get that right. You've got to make sure your Lambda has permission to send to the queue and read from the queue, etc. Always a fun time. And it was actually pretty cheap. So yeah, I was very, very happy with that. Lastly, where would I go from here? You know, this is a perfectly good solution for right now where we are as a company. We're a startup, we're hoping to scale. So things I would kind of look at next is a dead letter queue, like actually handling errors and being able to deal with that. We've just kind of been lucky so far that it's quite simple, that we're not having issues. Looking into DynamoDB streams, so we don't have issues with scaling up read and write. So far, it's low enough that we haven't had to worry. I should really tag my resources better, because that would help with cost estimations, things like that. And maybe I will have to learn Kafka one day, but not yet. So thank you very much. I'm Emily Melhuish, and it has been a pleasure talking to you.
Awesome. Thank you, Emily.